Hello everyone, thank you for listening my presentation. My name is Kai Liu. I'm from University of Florida. In this presentation, I will present my research project in wireless communication courses named Low Complexity Impulse-OFDM Design and Analysis for Medical Body Area Network Services. In my presentation, I will first talk about the Medical Body Area Network Service. Then I will focus on the challenges for communication problem in medical body area network services. To overcome these challenges, I will propose the low complexity Impulse-OFDM scheme. In the final of my presentation, I will evaluate the effectiveness of our proposed scheme. Now let's begin our presentation. So, what is the medical body area network? The medical BAN is one application of the body area network. The body area network focuses on the in-body or on-body sensor communications, or the sensors between the bodies and to the external devices. The usage of the body area networks include the body sensor network, the wearable audio systems, and the mobile device remote control and accesses. One important usage of the body area network is the medical applications. So nowadays, patients in the hospitals are attached to a lot of sensors, and these sensors are connected to the control center by using cables. These cables really making the patient really uncomfortable, and also making the monitoring and communication inefficient. By using wireless communication technologies, the patient can be free from these cables, and the doctor can also monitor the patient's healthy status automatically. Other services for the medical body area network include the vital patient data, healthy monitoring, or the fitness monitoring. The medical BAN is proposed by GE Healthcare, and GE Healthcare also petitioned the FCC to allow the use of the 3.36 to 3.4 GHz band for the medical body area network. The IEEE also set a task group to define a physical layer standard which complies with the FCC medical body area network laws. The target of the application in medical BANs is for low power consumption applications. Moreover, some medical applications like the ultrasound image systems really need a high data rate to transmit the images. Other health monitoring systems like the vital sign detections need a very low data rate, but need a very high reliability. The draft of the IEEE standard also defines the distance of communications and the network throughput, the latency, and the network setup time. By comparing the medical body area network to the existing communication techniques like the Zigbee, Bluetooth, Wi-Fi, and ultra-wideband, the medical body area network is focused on the low power side. But the medical BAN is really ambitious to achieving very low data rate to very high data rate. The low power and scalable data rate requirement of the medical BANs propose great challenges to the conventional communication techniques. So in this project, we try to design physical layout techniques to meet the communication requirement of the medical body area networks. We're utilizing the current physical layout techniques like the front-end antenna, filter, and amplifier used in the 2.4 GHz ISM band. We also try to combine the baseband OFDM and with the low complexity impulse radio ultra-wideband low complexity transceivers. Then we propose Impulse-OFDM structure for the medical body area networks. By utilizing the low complexity transceiver combined with the frequency domain processing approaches used in the OFDM technique, we can improve the spectral efficiency, data rate, communication reliability, and also minimize the overall power consumption and transceiver complexity. This figure shows the transmitter and receiver structures of the OFDM. In the first figure shows that the OFDM transmitter utilizes the IFFT modules to modulate the information in the predefined subcarriers. Then the DAC modules transform the digital signal to the analog domain and transmit it into the free space. In the receiver side, the ADC samples the analog signal to the digital domain, and the FFT and perform FFT to transform the time domain signal to the frequency domain, and then demodulate the information in the subcarriers, then obtain the binary data. This figure is the magnitude of the frequency point. Every point in this figure shows the subcarriers, and this is the phase information of the subcarriers. And this is the symbol amplitude of the transmitted signal. In the receiver side, we can the spectrum waveforms is shown in the left figures. The right figure shows the phase information of the received signal, and the information bit is actually modulated in the phase informations. To evaluate the performance of the OFDM transceivers, we conducted a Monte Carlo simulation to evaluate the beta error rate and the average phase errors of the OFDM on the different modulation schemes. So from the BER performance, we know that the BPSK achieves the best performance with slightly lower transmission speed, while the high order transmission modulation schemes achieve very poor beta error rate. To better evaluate the performance of the OFDM, we use the IEEE standard hospital band channels. In our project, we focused on the scenario S6, that is the body surface to external internal communications. That is the channel model 4, as shown in these figures. These two figures shows the channel impulse response for the 4 directions of the S6 CM4 channel model. By using the CM4 channel models, the beta error rate performance is really poor. Since the OFDM approach used in our project is really simple, and we don't have any channel estimation modules, so the poor performance is understandable. The most advantages of the OFDM system lies in its high spectrum efficiency and high data rate. But the disadvantage of the OFDM system is its high hardware complexity. It needs very high speed DAC to transform the digital signal to the analog domain, and needs the ADC to sample the signal back to the digital domain. With the development of the digital processing techniques like the DSP, FPGA, and ASIC, there are sufficient logical resources to process the IFFT and FFT in the OFDM processings. But the bottleneck of the system lies in its high-speed DAC and ADC. Because high-speed DAC and ADC consumes a lot of power and is really high cost. And this is also the reason that OFDM technique is only used in very complex communication systems like the Wi-Fi and the 4G LTE system. Another communication system is called the impulse radio ultra-wideband system. The purpose of the IRUW system lies in its high data rate spot, and it can achieve very high data rate using low complexity transceivers. And a lot of research have been conducted on utilizing the low complexity receiver to perform communication in IRUW system. But the cons of the IRUW system lies in its low spectrum efficiency, and it is unable to use the matched filter to improve the signal to noise ratios due to its sharper path. So in our project, we utilize the low complexity transceiver of the RRUW and perform the frequency spectrum processing of the OFDM, and we combine these two approaches together and call it Impulse-OFDM transceiver. We still use the sharp pulse as the transmitted signal to lower the transceiver architecture. But different from the RRUW, we use the different pulse patterns to transmit the information, like this figure shows. We actually calculate the corresponding spectrum template as shown in these figures as its fingerprint. So in the receiver side, we actually perform the spectrum matching between the polar coded patterns to the received signal. If there are some matchings, we can demodulate the information. This is our proposed Impulse-OFDM transmitter and receiver. In the transmitter side, we don't use the IFFT as in the OFDM systems. We place the time domain signals in different pulse positions, and then use the processor to transmit it, to convert it into the analog domain. We don't need to use the high power, the high compressed DACs. And the pulse generator can be implemented by using the SDR circuit or just using the digital jet to represent the sharp pulses. In the receiver side, we also can use the low resolution ADC to sample the high instantaneous SNR sharp pulses. Then in the digital domain, we perform FFT and transform the digital signal into the frequency domain. In the frequency domain, we perform spectrum matchings to the predefined spectrum patterns. Then we can demodulate the information bit. This is the spectrum matching result. As shown in these examples, we detected the pattern 3 achieve the lowest values. That is, we can demodulate the information as 0010. We also conduct Monte Carlo simulation to evaluate the performance of the OFDM to our proposed Impulse-OFDM. From this figure shows that the blue line shows the conventional OFDM. It cannot achieve very high performance in the high SNR side. By using our proposed Impulse-Radio OFDM, like by using the ideal process, like the red line shows, when SNR is larger than 9 dB, the BR is equal to 0. When using the Gaussian process, the performance is slightly decreased, but it still achieves very good performance in the high SNR side. Now let's talk about the demos use of our system to evaluate the performance of our systems. Now let's switch to the MATLAB. We have two functions. One function is our proposed Impulse-Radio OFDM modulation scheme, and the other one is the conventional OFDM. We transmit these figures and calculate the received two figures and calculate the BER and compare its performance. Then we write run our code. From this result, we can show that the BER by using the OFDM is really higher than our proposed Impulse-OFDM approaches. When SNR is equals to 15 dB, our proposed Impulse-OFDM can achieve the 0 BER. Now let's wait the result of MATLAB. It is still running. And this function is for the conventional OFDM. The first part is the transmitter, then the channel and the receiver. Then we output the image and calculate the errors. This is the Impulse-OFDM. This is the poly-coated spectrum patterns, but we only just need to calculate once. This is also the transmitter channel receiver output image and allocate calculations. There are totally about 700 lines of code. Now this program is finished. We obtain for proposed IR-OFDM schemes, we can achieve very low bit error rate. This is the result achieved by using the conventional OFDM. This bit error rate is really high. Now we also can check these two figures. Yes, this one. This one is obtained by the conventional OFDM approach. You can see there are some noisy points. And this one is obtained by our proposed approach. Although there is still some noisy point, but it is much clean than using the OFDM approach. That's all. Thank you for your attention.